Hi class, welcome to our lesson on 16.2. Yesterday we talked about what a sample is and what the population is. Now today we're going to talk about what does the sample actually tell us, or what does that mean for us. So again, a review, the population is the entire group of individuals. A sample is just a subgroup, so just part of that population for which we actually collect information. So a parameter then, class, a parameter is something that we know about a population or what we want to find out about a population. What we want to find out or what we already know about the population. Okay? A statistic is what we find out by doing a study or by gathering a sample. So an example of this might be to say, if I want to find out what percent of the student body thinks Mountain Dew is their favorite pop. Okay, I might do a study or a sample. So out of Hutchinson High School, there's 900 students, and I might sample 100 people. And I will ask them what they think, what percent like Mountain Dew the best. Maybe it's 30%. Okay, so from my sample, we would say that 30% is my statistic. Now, when the vote actually comes through and every single person votes here in Hutchinson High School, and let's say it is 26% think that Mountain Dew is their favorite kind of pop. Now this is the parameter because it's true of the whole school. It is known 26% of students think Mountain Dew is their favorite pop. Okay? When I did my sample or my study, I got 30%. Someone else might do a sample and they might get 27%. Another person might do a sample and they might get 40%. All of these are statistics because they are what's true about a certain sample. But this one is true of the entire population, so we call that a parameter. So here's an example. 20% of Americans are obese. A survey was taken from everyone who went to the doctor last week, and 25% were obese. Are these numbers parameters, or are they statistics? Well, this is true of the entire population. 20% of Americans are obese. That is a fact. Those facts, those are what we call our parameters. When we do a study or when we gather just a sample, just a subgroup of that population and run data on that, those are statistics. So this 25%, that wasn't the whole population. That was just a few people that went to the doctor last week. So in this sample, we would call this our statistic. A statistic is always from the sample. A population has a parameter. So the PP, population with the parameter, SS, the statistic goes with the sample. Okay, so do samples always give good data about the population? So take a look at this example. Suppose that in fact, unknown to Gallup, Gallup is an agency class. It's a U.S. agency that is in charge of gathering data and doing a bunch of statistical work. So it's a nationwide organization, a very big program. So in this study, exactly 60% of all adults have bought a lottery ticket in the past 12 months. So this is not a statistic. This is a parameter. This is true of the entire population. It is a fact. 60% of all adults have bought a lottery ticket. You could bring that home to the bank. That is a known fact. So this is a parameter. Now, Gallup didn't know that, so they want to predict. I wonder how many people are going to buy a lottery ticket this year. Since Gallup didn't know that fact, they conducted 2 studies to determine the number of adults that have bought a lottery ticket in the last 12 months. So they're going to do a sample. They're going to not gather the whole population, but they're just going to get a subgroup, just a sample. And notice what happened. They got a simple random sample of 100 people 3 different times. And in those samples of 100, 56 bought a lottery ticket, 56 out of 100, so 56%. 46 or 46% bought a lottery ticket, and 61% bought a lottery ticket. Remember, 60% is what's true of the entire population. So our samples should represent what is true of the entire population, so the closer we get to 60%, the better the sample was. This was probably a pretty poor sample. It had a lot of bias in it. That 46% is quite a bit of ways away. So as we look at this, we can see how the spread is pretty far away. Okay, we would want to see statistics closer to 60%. So this one obviously being far away. These two are closer. But take a look at the next slide. What happens when we increase our sample size? On this one, it's 100. On this one, they got a sample size of 1523. 1,523 people. How Gallup got that number, I'm not sure, but that's how many people were in their sample. And now, look at how less of a spread there is. This one is about 61%. This one, 62.5%. This one, 58%. Notice how they're much, much closer to that 60%. And hopefully that makes sense. When you gather more and more people, your sample size is increasing, so your statistics should be closer to your parameter. The larger the sample, the more input you have from everybody, and so the closer you're going to get to the actual population parameter. So what these slides are telling you, class, is if you want to increase your samples, if you want to have a better indicator about what the actual population parameter is going to be, increase your sample size. Here we have a sample size of 100. Here we have a sample size of 1523, and you could tell that the variation was much smaller. We were able to closer get an accurate picture about what the actual parameter is going to be. So increase your sample size is always a good idea when you get samples. Okay, now talking about the margin of error. We're going to be calculating margin of error, and we're going to be using this formula right here. It looks kind of complicating. It really isn't as bad as it might look. I'll show you how to do that in the next few slides. So your margin of error, class, what it is it's kind of like your S in last chapter. It's that typical error. It's like, I predict that this % of people are going to vote this way. But I am going to account for the fact that I might be wrong on that. I might be off a few percentage points here and there, but your margin of error kind of covers you a little bit just in case you're wrong. So we'll talk more about this, but you know, you want to have as little error as possible. If you have a big error, it means you're not very confident in your statistic. But the smaller your margin of error, the more confidence. I'm sure that the actual population parameter might be this much % because my margin of error is very, very small. So you want a small margin of error when you do these samples. So to decrease the margin of error, once again, take a bigger sample. The more people you have in your sample, the closer it gets to the actual population parameter. So to take a bigger sample, that's how you decrease your margin of error, which again is a good thing. You want a small margin of error. Margin of error is determined by the sample size, not the population size. So make sure you understand that. We might have statistics done in the United States, and we might have statistics run in China. Even though China is a lot bigger country than we are in population, if we take a sample size of 1,000 here in the United States and they take a sample size of 1,000 in China, it doesn't matter that China has a much larger population. The margin of error would be the same because the sample size is the same. So that's what we pay attention to when we talk about margin of error. It's the sample size, not the population. Okay. So here's what this means. This is a margin of error of 0.09, which is kind of like 9%. If you move it over 2 decimal places, it'd be 9%. It says if we took many samples using the same method used to get one sample, 95% of the samples would give a result within plus or minus 9 percentage points, or 0.09, of the actual truth of the entire population. So let's go with my Mountain Dew example that I had at the very beginning of class. I took a sample, and let's say I got 30%. So we would call that 0.3. Okay, 30% is 0.3. And then my margin of error, let's just say I got my margin of error to be 5%, okay, which is 0.05. I would say that 0.25 to 0.35, I am 95% confident that the population will be between 0.25 and 0.35. If I did this sample 100 times, 95 of my samples would come between these two values. The other 5% might be less than 0.25 or might be greater than 0.35, but there's only 5 out of 100 of those. 95% would fall between these two ranges. Okay? we always use 95% confidence. There are other confidence levels, but most oftentimes when you see in the real world, when you read in the newspaper or when you read on online articles, when they do certain studies, it's almost always done to 95%. So that's why we do that in this class. Okay, so let's just think about this one for a second. If you do one survey and sample 500 people in a population of 2,500, versus another survey where you sample 500 people in a population of 10,000 people, which survey would have a larger margin of error? So if you think of it this way, this is about the size of Dassel. Okay? Let's say you took 500 people in Dassel to take a survey. And this is a little bit smaller than Hutch, but let's say this is about Hutchinson size. And you're going to take 500 people in Hutchinson to take a survey. Which survey will have a larger margin of error? So margin of error is bad, so we want to increase the sample size to have a smaller margin of error. But if your sample size is the same, the margin of error is determined by the sample size, not the population size. So we don't really care that Hutch is bigger than Dassel. All we care about, class, is their sample size. Here we have a sample size of 500. Here we have a sample size of 500. So who will have a larger margin of error? The margin of error will be the same. The sample size is the same, so the margin of error will be the same. So make sure you recognize that. Okay, confidence statements. We're going to make some confidence statements here coming up. You're also going to have some on your worksheet. You're also going to have some on your test. Confidence statements include confidence level, which is always 95% in this class. In AP Stats, you might do a different confidence level, and Mrs. Beefert will teach you how to do that. But for now, we always talk about 95% confident. We talk about the confidence interval. I'll explain that in just one moment. And then we also talk about the parameter, which is what we want to find out about the actual population. Again, we always deal with 95%, but it's nice to know that if you have a bigger confidence level, let's say you want to be 97% confident or 99% confident, that means you have to open up your margin of error. It's like if you're 95% confident that it's between this value and this value, well, if you're 99% confident, then you have to open up your margin of error, because just in case you're wrong, you got to cover yourself on both ends. So if you're going to be more confident, you got to give yourself more wiggle room to be off a little bit. So you got to open up your margin of error. Okay? All right. Here's an example of a confidence statement. Let's say we asked a bunch of teenagers, do you approve of gambling or do you not approve of gambling? And we got something that looks like this, for example. We would say that we are 95% confident that the interval from whatever to whatever, this is the confidence interval, so 47% to 58%, but always write this as a decimal, so 0.47 to 0.58 captures the true proportion of teenagers that approve of gambling. And this is the parameter, this is what we want to find out about a population. So we're thinking it's somewhere more in the middle, more around 52 or 53%. We think that number of people, teenagers, approve of gambling, but our margin of error is such where we're going to say from 0.47 to 0.58. We're 95% confident of that. If we did 100 samples, 95 of them would fall between this range. The other 5% would be outside that range. Okay? Let's practice this. A recent study was done by the Mayo Clinic. They wanted to find out how many females between the ages of 18 to 23 exercise 3 times a week. They gave a written survey to 300 randomly selected females between the ages of 18 to 28 and found that 123 exercised 3 or more times per week. Okay, so our population, who or what are we choosing from? Looks to me like our population are females. We don't care about males in this study. All we care about is females between the ages of 18 and 28. That is our population. Females, ages 18 to 28. Parameter, what do we want to find out about them? We want to know how many of them exercise 3 times a week. How many exercise 3 times per week? Okay, keep on going down. Our sample Our sample size is 300 randomly selected females. So our sample size is 300. And we should say, yeah, 300 will work. Here we go. Our statistic, round to 4 decimal places, our statistic is what we find out or what we know to be true of our sample now. Remember how the sample always goes with the statistic. So we know that in our sample, 123 exercise 3 times a week. So 123 divided by the total is going to be our statistic. So if you take 123 and divide it by 300, round to 4 decimal places, which in this one is 41% or 4100. As a decimal is 0.4100. When you take 123 divided by 300 in your calculator, you get 0.4100. Okay, so we're saying that we're predicting that 41% of the entire population exercises 3 times per week. We might be off. Maybe it's 40, maybe it's 39, maybe it's 43. We might be off, but we're predicting that this 41% of females exercise 3 times a week. And we got that from our sample. But we know we might be off. We're predicting we're going to be off, so that's why we have a margin of error. So we're going to use this formula that's found on the front page of your notes. So here it is. It's plus or minus 1.96 times the square root of p hat, right? And that is our statistic. So our statistic is 0.41. So 0.41 is going to be multiplied by 1 minus p hat. And so if you take 1 minus 0.41, you're going to get 0.59. So 0.59 goes here. So basically, class, 41% is this, and what is left to get to 100%? It's 59%. So these two right here will always add up to equal 100%, or they will always add up to equal 1 when we put it as a decimal, which in this formula we always write it as a decimal. So know that on your test, these two will always, always, always add up to 1, or those two make 100%. And then you divide it by your sample size. And your sample size in our case is 300 females. So we divide by 300. So in your calculator, take 0.41, multiply by 0.59, divide it by 300, square root that number, multiply by 1.96. Whew! We get plus or minus, rounded to 4 decimal places, 0.0557. That is our margin of error, 0.0557. So we're saying 41% exercise 3 times a week. But if I'm off, I'm not going to be off by more than 5.5%, 5.57%. So I'm going to give that as my window. So your confidence interval, what we're going to do is we're going to add and subtract the margin of error to the statistic. So it's 41%, or 0.41 minus 0.0557, and 0.41 plus 0.0557. That's why you have this plus and minus here. That's why you have that plus and minus there. You add it to the statistic, and you subtract it from the statistic. So when you subtract it, you get the number 0.3543. And when you add it, you get 0.4657. So, the confidence statement, and you say this loud and proud because you're proud of all your work. We are 95% confident that the interval from 0.3543 to 0.4657, those will always be as a decimal, captures the true proportion of what you want to find out. Captures the true proportion of women or females ages 18 to 28, that exercise 3 times per week. Okay? So if we did 100 samples, we would predict that 95 of them will give this result, somewhere between 35% and 46.5%. Okay, it'll be somewhere in there. So that's how we're going to write it for our worksheets. That's how we're going to write it for our test questions. Let me know if you have any questions on that. That's a big part of your next test, is to go through this whole entire slide. Okay, so you'll get some practice on that in your worksheet. You'll get some practice on your review, of course, as well. All right, there's your worksheet. Let me know if you have any questions on that when I see you tomorrow.